A penguin must maintain a core internal temperature of 38 degrees Celsius, but it lives in an Antarctic environment where the air drops to negative 57 degrees, accompanied by winds whipping at 40 meters per second. Surviving on that freezing land requires a thick, air-filled, open-cell structure to trap body heat. But to hunt, penguins must dive. That requires a thin, highly compressed, waterproof profile to eliminate the positive buoyancy that would otherwise keep them trapped at the surface. Despite navigating these conflicting physical requirements, the penguin's coat achieves an overall thermal conductivity of roughly 1.93 watts per meter squared Kelvin. They resolve this thermal paradox not by carrying bulk mass, but through a highly organized, dynamic, dual-layer biological architecture. The outermost layer of the plumage is made of stiff, pennaceous feathers. This acts as a windbreaker and a waterproof barrier against the ocean. When preparing to dive, the penguin uses muscles attached exclusively to the main shaft of these feathers to lock them down, sealing out the water and compressing the coat. The actual source of the penguin's extreme thermal insulation sits entirely underneath that shell, in a structure called the afterfeather. Attached to the base of the main shaft, the afterfeather branches into a central ramus. That ramus supports thin barbs, which in turn support thousands of tiny spiraling barbules. Looking at this micrograph of a Pygocellus popua feather, we can see the exact breakdown. The prominent afterfeather at the bottom extends its barbs, and the magnified sections reveal how densely those spiraling barbules are packed together. The animal has no direct muscle control over this intricate underlayer. Its immense insulating power relies completely on passive, self-organizing microscopic geometry to stop heat from escaping. To understand how that geometry works, we have to look at the first fundamental mode of heat transfer threatening the penguin, natural convection. This is the process of warm air rising and cold air sinking within the plumage. Natural convection can only occur in a fluid, like air, if a specific dimensionless value, called the Rayleigh number, exceeds approximately 1700. To calculate this, the Grashof equation looks at one critical geometric variable, characteristic length. Inside the coat, the distance between barbule layers is exactly 1 millimeter. This gap drops the Rayleigh value to 0.2, far below the 1700 required for currents. By strictly limiting the physical spacing between its feathers, the coat makes convective heat loss impossible. That leaves the second thermodynamic challenge, radiative heat loss. This is the direct transfer of thermal energy from the warm skin out to the cold Antarctic air. This schematic side view shows horizontal barbule layers stacking 24 millimeters high. The Stefan-Boltzmann equation dictates each layer halves radiant heat loss. By stacking exactly 24 shields, the skin's radiant heat loss plummets from 78 watts per square meter down to just 3.1. The final mode of heat transfer is conduction. The coat minimizes this through high porosity. Most of the volume is simply immobilized air, which has exceptionally low thermal conductivity, held within a sparse open-cell keratin meshwork. The internal architecture of the feather is a deterministic engineering solution. It systematically neutralizes conduction, completely eliminates convection, and severely restricts radiation. But even an optimal coat only protects the core of the body. The penguin's flippers and feet remain completely naked, exposed directly to the harsh, freezing water and jagged ice of the Antarctic. To prevent a catastrophic heat drain from these extremities, the penguin utilizes a highly specialized biological plumbing system. This structure is known as the rete mirabile, which translates to wonderful net. It acts as a countercurrent heat exchanger. As warm arterial blood flows outward toward the feet, it passes through a dense interwoven network of veins carrying cold blood back to the heart. The heat transfers directly across the vessel walls, moving from the arteries into the veins. The cold blood is warmed before it reaches the core, and the feet are kept just above freezing. This recycles the animal's heat and preserves its metabolism, without requiring bulky insulation that would restrict the physical mobility of its extremities. We know the afterfeathers lack direct muscle attachments. So how do they achieve the perfect 1 millimeter gaps required to block convection and shield against radiation, completely passively? This scanning electron micrograph provides the answer. Projecting from the individual barbules are microscopic forward-facing hooks known as cilia. These cilia utilize a stick-slip mechanism. They catch and entangle with the cilia on neighboring barbules, allowing them to slide in only one direction before locking into place at a highly specific distance. The moment the penguin emerges from the water and raises its main feather shafts, this mechanical entanglement forces the after feathers to instantly self-organize into precise, uniform horizontal layers. Overlaid onto this geometry is a secondary surface defense. The outer feathers contain nano-sized pores, which the bird coats in a specialized preen oil secreted from a gland near its tail. This combination of surface chemistry and texture renders the outer shell super hydrophobic. Water droplets bead up and slide off the bird before the sub-zero temperatures can crystallize them into ice. The penguin operates as a fully integrated thermodynamic shield. It survives extreme environments by combining nanoscale surface chemistry with exact macroscopic geometric layering. Human engineering typically approaches extreme cold by applying static, bulky foams or relying on energy-intensive active heating systems. The penguin achieves the same result with a passive, adaptive, multi-layered material. Material scientists are now attempting a direct biomimetic translation of this biology, developing what is called an adaptive Janus composite film. This synthetic film replicates the penguin coat. It traps insulating air, but utilizes metallic layers to actively modulate thermal radiation. The film incorporates vanadium dioxide. Based on ambient temperature, the material changes state, acting as a metal or insulator. In cold environments, the film absorbs 94.5% of incoming light. When the environment warms, it shifts to reflect 90% of the heat. Because of its unique structure, this material can also modulate broadband microwave signals, all without drawing any external power. Bypassing our heavy reliance on mechanical heating and cooling requires better materials. The solutions already exist, waiting to be decoded from the precise geometric architecture of evolutionary biology.